Good morning, everyone. So my name is Greg Hankins. I usually talk about 100 gig, and today we're not going to talk so much about 100 gig, although I'll probably have to mention it a couple of times. But we're going to talk more about the router architectures and things that we're facing. So at the June NANOG, we did cover optical technology in quite a bit of detail, so stuff that's going on the wire. Drew Perkins had a really good talk about all the optical developments, and then I talked quite a bit about 100 gig technology and first and second generation things that we're doing, but we really haven't talked about hardware architectures in detail. I think since probably NANOG 39 in Toronto, we had a really good BOF, and that was actually the inspiration for the title of my talk about pushing the fib limits. So I turned it into a more generic talk about just pushing the limits and all the things that we're trying to do. Interesting text there. Sorry, that kind of ran across the screen. So anyway, in this presentation, we're going to talk about all the things behind the packet processing. And this is a little bit of a weird angle for a picture, I think. But when I was talking to some of our ASIC engineers, their comment was, well, we always look at the line card from the front, and we always look at the ports, and we don't really look at the back end and the stuff that we're doing in hardware. So it may be a weird angle, but I think it's kind of appropriate for this presentation. So if we kind of look at the challenges, the basic challenges, trying to boil it down into what we're trying to do. On one axis, we have things like lookup capacity and forwarding capacity, and this is the routing table and all the things that we're trying to do in the ASICs with multi-protocol forwarding. We have growing internet routing tables and VPN tables. We have the IPv4 deaggregation and the IPv6 adoption, so we're not really sure what's going to go on with the routing table growth. And on the other axis, we have port density and the fact that we're trying to do line rate 100 gig, which is one packet every 6.2 nanoseconds that we actually have to look up. So if we put that all together, we can't do everything. We can go either very complex, but that limits our port density, or we can do really high port density, but that limits the complexity. So it's really a trade-off between the components that we're trying to put into the hardware with the available technology, and then the risk is throwing in the kitchen sink and trying to make it too complex, because that just limits the density completely. So if we look at a basic router forwarding architecture, this is the way that our card is laid out, but virtually every router that I've looked at in the past 10 years at least has a very similar architecture. Some components may move around. You may have a separate MAC or a separate PHY or combine some memories, but basically there's a traffic manager, a network processor, and some memory components. System RAM, which is not really the focus of this presentation, system RAM just uses regular DRAM, and there's not really any I guess, pressing or new developments around system RAM. System RAM is growing, and we can put a lot on the CPUs. The memories that we really want to talk about are the packet lookup memories, which is typically built out of TCAM and some sort of other RAM, and the packet buffer memories. So for packet lookups, we're trying to do at least 100 million packets, 150 million packets per second lookups, hopefully more than one port on a card. And for packet buffer memory, we actually need at least 200 gigs of throughput in and out of the memory. So that's a pretty high performance requirement. And then we have some chip-to-chip interfaces, which are basically the SerDes links or some sort of other links which tie the components together. And those are typically in the range of 3.125 up to 25 and 28 gig links coming soon. Okay, so let's talk a little bit about memory technology developments and things that are going on there, and then we'll talk a little more about the ASIC technology. The memory challenge really is that packet rates have greatly exceeded the memory read rates. And for people that are really into the hardware, this is TRC, the row cycle time. So that's really the limiting factor here. We would like to have lookup and buffer memories that have about a 1 nanosecond random read rate, and also obviously for buffering, we'd like to have a nanosecond write rate. We don't have that today. Dynamic RAM, while it is dynamic and it is random access memory, doesn't actually mean that you can randomly access the memory at the same time anywhere you want. Memory has these inherent constraints where you can read or write something, but then you basically have to wait a little bit of time before you touch that same bank. So that's called bank blocking. You can't read the same bank over and over again or write the same bank over and over again. So that really has some challenges in how we have to lay out the RAM. And since it's inherent to RAM technology, it applies both to on-chip and off-chip solutions. So just kind of to give you an idea, today's solutions that we have are dramatically slower than we would really like. So we have possibly around 48 nanoseconds for random access, sort of commodity DRAM, maybe around 20 nanoseconds for specialized off-chip, which would be RLDRAM, and then we can actually get into single-digit nanosecond random read rates if we put the memory on the actual chip. So really, the requirements that we have for lookup and buffering memory are twofold: fast and big, and we would like to have those two things together. So for fast, we actually have to store everything that we need to look up for a packet in hardware. We want to do this at line rate. So like I mentioned before, for 100 gig, that's 150 million packets per second, or about one packet every 6.2 nanoseconds. We would like to have multiple ports on a network processor to give us more reasonable density than just single port 100 gig cards. And in fact, we actually have to do multiple packet lookups per packet. So we have to look up, in some cases, possibly 2 or 3 things in a packet, which takes 2 or 3 cycles. In terms of big, obviously we're putting more and more stuff into the router. So we have MAC address tables, which can now be your sort of general layer 2 table. Then we have all these VPN technologies we're putting on top of that, VPLS or PBB or something like that. We have the IPv4 FIB, v6 FIB, that's unicast, multicast, VPN routes, ACLs, QoS policies, and then also we want to have obviously deep buffering because we need multiple hundreds of gigabits of sustained memory throughput. If you look at a gigabit of RAM or a gigabyte of RAM, that's only about 80 milliseconds buffering at 100 gig rate. So we obviously have to have a lot more on there. And then we'd actually like to have thousands of queues per port and do all sorts of queue management and hierarchical QoS and things like that. So the buffer memory can get quite complicated. So what we really need is a big fast elephant, but unfortunately those things don't exist. So we kind of have to build our own big fast elephant out of available component technology. So if we just look at the available memories that we have, there's really 2 kinds of memories. There's TCAM, which is a search memory, and then there's a bunch of different kinds of RAM, which is really storage memory that we're trying to do searches on really fast. So I don't want to read you the whole table, but a couple of things that I want to point out is that the TCAMs that we have, they give us fantastic access speeds. Unfortunately, the density is a little bit lower than we need, and the cost per bit and power consumption are much higher. If we look at technologies like static RAM, it's really, really fast, but unfortunately, the density isn't there, and also the cost per bit is significantly higher. And then some of the DRAM technologies, DDR, that's just your standard sort of desktop computer memory. It has really, really good density, but unfortunately also has the highest latency. So that doesn't work out either. Then we get into some more specialized memories like RLDRAM and GDDR, which is the graphics DRAM, and those have again, really good high access speeds. Density is really good, but unfortunately, it just doesn't work in terms of some of the things that we need because it is specialized memory. So it doesn't always work out. Just because a component's available doesn't mean we can integrate it. And I'll talk a little bit more about that in the next couple slides. So we've had to put it all together. There's basically a couple mechanisms to do longest prefix matching. There's your traditional CAM technology and then some sort of combination of RAM technology. And the way that a CAM works is basically you ask it an IP destination address, hands you back some sort of index into the next hoc table, and it's a very simple search. We like CAMs because the search latency is fixed, the throughput is pretty high, you have fixed and bounded add-delete times. The partitioning is very simple, so if you have a CAM partition, say, that holds 1 million v4 prefixes, it will hold 1 million v4 prefixes under all conditions because you have exact partitions in the CAM for that capacity. So the ordering and the layout is very simple to do. You just order the data in terms of longest mask, and that's how the lookup works. When you have a RAM-based architecture, what you're basically trying to do is take an ordered data structure and do a lookup on that data structure in hardware. You're just moving it from software into hardware to make it faster. So it has a lot of properties that we like, but also some challenges. One of the challenges is that there are a bunch of different search algorithms to do tree traversal. This is nothing specific to hardware. Like I said, we're just taking some sort of tree algorithm and making it work in hardware. Sometimes those are patented, but unfortunately, each algorithm also has trade-offs. So, for example, one algorithm might use hashing, and then you have to deal with that hashing, and that actually affects the capacity of the memory system. So, like I said, with CAM, it's very easy to say, we can hold this much memory in our routing table. With a RAM-based system, unfortunately, it's variable, and we can talk about worst-case scenarios, and we can give upper and lower bounds, but it's hard to give you an exact capacity number. So in terms of memory architecture solutions, I think this is kind of where the industry is going. I think we used TCAMs for a long time. We're going to have to go dramatically faster, I'm sorry. But basically, I think we're going to see new architectures that combine these SRAMs and DRAMs so that we can get a large number of banks where we can do parallel searches. And then also, and I'll talk about this in the next section, I think what we're going to see is people integrating packet lookup memories actually into the ASICs. So that'll give us a lot faster lookup speeds. Remember, if we do on-chip lookups, we can actually get down into the single nanosecond lookup ranges. And the thing that I also want to remind people of is that we have to have technology that will last us and be around for at least 5+ years. The graphics technology in particular is moving so quickly that we just can't put that stuff on a line card. So if you go into a Best Buy, for example, I think every time I go in there, there's some new graphics card that uses some new memory technology or something like that, right? So that industry is moving really fast. I don't think you would like it if we gave you a new version of our line card every 3 or 6 months. I just don't think that would work. So in terms of buffering, it's a tough challenge to get that much throughput in and out of buffering memory. I think the DDR4 speeds that are coming will give us a lot faster memory throughput. But basically, the way that buffer management works is that there's no algorithm out there like there is for tree traversal. It's a very specialized and proprietary technology that vendors use. And I think we might possibly see that moving into its own custom ASIC. So it's kind of technically feasible to actually just design a custom buffer memory chip that works a little better than commodity DRAM. Okay, ASIC technology, this is really the challenge, is we're trying to do a lot of lookups on a packet. It's really complex, and we have to actually look pretty deep into a packet. If you look at all the things that we're trying to do with layer 2 forwarding, IPv6, v4, multicast, unicast, broadcast, .1q, trill, SPB, PBB, MPLS, all these things that have their own specialized packet header, we have to be able to look up all that stuff at line rate. Lag load balancing in particular is very complex and means we have to look really far into the packet, possibly into VPN headers and pass multiple labels and things like that. We want to do things like OAM hardware timestamping now to give you accurate counters. We also want to have a ton of statistics counters, so virtual interfaces, and also aggregate VLAN counters in particular are a tough challenge to implement in hardware. And basically, like I mentioned before, it's all about integration. So the more stuff we can put into a chip, the more scalable we can make the system. There's a couple limitations. We can basically use a lot of chips in parallel, but that means higher costs, much higher power, higher heat dissipation, and overall lower MTBF for the system. So we're looking at next generation technology that I have. I'll show you the next slide. Basically, we're moving to 45 and 32 nanometer process technology, counting on 22, which is coming up, to be technically feasible. And then we also have to talk about the chip interconnects, because we're still limited a little bit in the component interfaces that we have. And then just to give you an example, on our 100 gig card, we actually use over 100 integrated circuits. So that's just a ton of circuits to manage and a ton of components to manage, and we need to reduce those components. So we look at where process geometries are going. Fortunately, we're still following Moore's law, and I think some of the projections I saw think that we can still meet that well past 2015. So we don't see any sign of Moore's law being wrong anytime soon. And basically what that allows us to do is continually increase the number of transistors and also the number of gates that we can put into the ASIC. So the transistors are basically the building blocks that we use to make gates. So the more transistors we can put into an ASIC, the more gates we get and the more logic we get out of it. And unfortunately, it's kind of every vendor has their own capacities, so I just gave you an example from some of our ASICs because we can't actually tell you what the ASIC vendor capacities are without them getting somewhat upset of us. But basically you can see that we're coming up on chips that approach 5 billion transistors and 50 million gates. So that's pretty exciting in terms of what we can do on the actual ASIC. And then there's also ASIC technology evolution. This is really cool. So what we're seeing basically is ASICs that are traditionally a 2D package. So you have one really big ASIC on a really big chip and that's your component. Where we're going is actually what's called a silicon interposer, which connects multiple chips on the same package, and then eventually we'll actually go to 3D packaging. And 3D packaging, I think, is ultimately very cool and will allow us to do the most things, because it really just combines two ASICs into one actual package. So in terms of advantage, the advantage really is that we have much shorter interconnects. Remember, we want to get to that 1 nanosecond or single-digit nanosecond latency for memory. These packages will actually give us that, because we can put memories and packet processing technologies on the same ASIC.
One real quick question. What do you see the line card pitch for the 3D packaging?
That's a really good question, and that's a very ASIC-specific question that I really don't know the answer to. So I don't know all about the pitch and balls and stuff like that. I'm really just trying to give you an overview of where the technology is going. The other advantage is that it gives us a lot lower power consumption, although it does have a lot more heat and signal density in the same place, right? Obviously, we're taking a bunch of different ASICs, putting them in the same place, so we're going to have a lot higher heat in that same place. And this is a picture from an IBM 3D package. It just looks like a regular ASIC, so there's nothing special really in terms of the ASIC that we have to do. It's just going to be a 3D ASIC. Okay, chip interconnect signaling. I showed this slide when I was talking about 100 gig last time, but basically we need faster component signaling technology in between the ASICs. And as far as integration, this is a challenge, because if you look at current technologies, you have them either optimized for ASIC technology, so logic driven for things like network processors, or memory technologies obviously optimized for memory. So we can't really do the same thing in the same ASIC. We can't do two different things in the same ASIC. We can't do memory and logic in the same ASIC, because the ASIC isn't optimized for both of those at the same time. So the 3D chips will actually allow us to do both of those things in the same package. And then you may ask, well, okay, so you said that 22 nanometer technology was available in 2011. Why aren't we using that? Well, you have to also look at the way that ASIC technology works. Basically, vendors make the transistor density their focus first. And then the rest of what's called the logic library is developed afterwards. So we actually have to be able to have all those components in order for us to put stuff on the board and to be able to integrate it. Okay, technology integration. This is just kind of an example to show you how challenging it is to put all this stuff on a board. This is a picture of our current generation line card, and you can see that in terms of the ASIC density, there's just no room on there. And in fact, our next generation card is going to be a motherboard and then a full-length daughter board that just covers the whole card. So we're trying to put more and more stuff on there, and like I mentioned, the 3D ASIC technology will give us a lot more options in terms of better board real estate utilization, shorter interconnects, less power consumption, and things like that. Okay. Summary. Okay, we're doing well. So alternatives to fib scaling, there are some out there. Like I said before, Moore's law still is holding true, so we think we have a couple more years at least on that. There's a couple different software fib aggregation technologies that have been proposed. There's a really interesting paper that I encourage you to go read. This basically talks about, okay, let's take the whole fib and then optimize it and only put the stuff that we need into the actual hardware. And then there's what's called simple virtual aggregation, which is a much more simpler approach, which basically just says put a default route in the hardware and maybe a couple other things that you need. So it's a much simpler algorithm. Open flow is software-defined networking or programmatic networking. That's a whole nother topic and possibly a can of worms. And then we also have some tunneling mechanisms like Lisp, which has been proposed, but as far as I know, has turned into more of a data center technology than really a fib scaling technology. So, okay, in summary, we really would like to give you cards that you can use for at least 7+ years. We want to do multi-protocol forwarding, high density 100 gig with CFP2 optics. We want to have a scalable and a flexible fib, that's the global routing table, and a lot of VPN routes. It's a tough balance because we have to make trade-offs, and technology capabilities dictates what we can do with the functionality and the port density. And eventually, we'll have a bunch of things that I think will allow us to do higher capacity and will allow us to scale in the future. So we have multi-100 gig packet processing ASICs, and then custom lookup and custom buffering memory solutions, and then the cool 3D ASIC technology that I talked about will allow us to do all that stuff in the same package. fast.
Thanks, Greg. Thanks for that. Questions? Let's take a question or two, and then we'll get to the break. Going? Come on, I know somebody has some questions.
The one time I'm talking on the mic, not asking hard questions. The Wi-Fi is being investigated right now. The note that I just sent to the list should provide some additional detail. We're very sorry, but we're trying to fix it. Thank you.
Hey, that wasn't a question, man. Come on. All right, I guess it's break time. Thanks, Greg.